everyone, and once again we are at CMOS RF integrated circuits. This is the third lecture, and today's agenda will be to discuss the maximum power transfer theorem. Now, the maximum power transfer theorem, I am sure all of you who are studying this course have already studied it once, at least once before, and it is like this. If I have a source and there is a source resistance, then maximum power is transferred if the load resistance is equal to the source resistance. So, it is a very simple theorem. But it is widely misunderstood, especially when you study it at your undergraduate level. There are a lot of misconceptions that arise. The first misconception is this. I will not talk about the misconception, let me elucidate this theorem for you. The first most important thing that you have to understand is that the source resistance is a part of the source. The source resistance is an integral part of the source. You cannot have the source without the source resistance. It is unfeasible to think of a voltage source without any source resistance. So, this source resistance represents the source resistance that is inside the voltage source. It is unavoidable and you cannot change it. So, this is number 1, that the source resistance cannot be decoupled from the source. Now, once you understand that, then the question is, what should the load resistance be? What should R L be to get maximum power transfer? And the answer to that is R L should be equal to R S. Okay. So, it is important to understand that the source resistance is part of the source, and as a result of this, only a limited amount of power can be transferred. If the source resistance was 0, then you can transfer whatever you want, right. I mean, if this resistance happens to be equal to 0, then you choose R L to be 1 ohm, you choose R L to be whatever you want, and that much amount of power V squared by that much amount of power will be transferred to the load. So, there is no limit if the source resistance is 0, but the source resistance is non-zero, it is finite non-zero number of ohms. So, that is the critical most important point over here. Okay. Now, if we talk about impedances and not resistances. So, if this was not R S, if it was Z S, and if this was not R L and therefore, I want a Z L, then the relationship is Z L should be conjugate of Z S for maximum power transfer. So, all this is fine. This is the basic idea. Now, in the last class, we studied reflections because of transmission media, etc., and we concluded as follows, that if I have a source then to avoid reflections, I would like to have RL to be equal to Z naught. To avoid reflections at this interface, I would like RL to be equal to Z naught, and to avoid reflections at this interface, I would like RS to be equal to Z naught, which eventually means that RS should be equal to RL, should be equal to Z naught. Now, this is just a coincidence. It also naturally gives us maximum power transfer, but let me remind you that is just a coincidence that it so happens. It so happens that when RS is equal to RL equal to Z naught, I not only get maximum power transfer, I also do not get reflections echoing back and forth. It is also easy to understand. If I have a black body over there in front, if you have a black body which absorbs whatever you send it, does not reflect back anything, then it should be absorbing the maximum power also. So, through network theory you can show all this, that these two concepts are interrelated. For us, it makes no difference that maximum power transfer leads us to no reflections. No reflections is important for us, maximum power transfer is also important for us. Okay. When we are talking about an RF system, we have an antenna, and then we have an LNA, a low noise amplifier. We want maximum amount of power possible to be received on the low noise amplifier. Why? Why do I want maximum power on the signal to be received onto the LNA? It so happens that maximum power received on the LNA also means that there are no reflections. That is a coincidence. That is a coincidence. Next important thing is that the LNA has a finite amount of power gain . So, the output power of the LNA is the input power times the power gain of the LNA. Now, if the input power is maximized, then the output power is maximized naturally. So, this is also very important. Why is this important? Because to start with, the input power is very small, the power received on the antenna is very small. We are talking about nanowatts of power. Okay. So, 0 dBm is 1 milliwatt of power. If I want to make a receiver for a cell phone, when you are furthest from the base station, let us say I am talking about GSM or something like that, then typical numbers could be as low as minus 100 dBm. So, a GSM phone has a sensitivity of minus 100 dBm, which is 10 power minus 10 milliwatts. And how much is that? That is 0.1 picowatts. All right. So, that is a very low amount of power that your LNA has to be sensitive to. Your low noise amplifier has to be sensitive to that extremely low amount of power hitting the antenna. Now, what that means is, if I do not do maximum power transfer, then it is even worse for the LNA. So, I want to transfer as much power as possible from the antenna to the LNA and then moving forward to the mixer, etc. we are talking about extremely low power levels over here. So, 0.1 picowatt, if this antenna is 50 ohm antenna, then what this relates to, 0.1 picowatt is 10 power minus 13 watts is equal to V squared by 50 ohms So, it is something like this, 2.2 microvolts. So, that is the amount of voltage that you want to sense for this kind of a power level, that is the amount of voltage that you have. Okay. So, that is why maximum power transfer is important for us. Now, you have all studied your circuits, MOSFETs. I am going to jump the gun over here and I am going to assume that you know the MOSFETs, although in this course we are going to talk about MOSFETs later on, but let me just give you a flavor of what is coming. So, you have all designed amplifiers, and amplifiers, low noise amplifier is some kind of an amplifier presumably. So, the input of an amplifier, what you have designed before typically would look like this, or if you have designed a differential amplifier it would look like this. Etcetera, etcetera. So, there is a load to this. And so on and so forth. So, this is probably how the input of the amplifier looks like. Now, as far as this kind of a circuit is concerned, if you look at the input impedance is infinitely large, or is the input resistance infinitely large? What is the input impedance of this? Let us say differential mode half circuit. So, you forget about all this. So, this is the input small signal small signal model of your differential mode half circuit of your amplifier. This is how it looks. Question is, what is the input impedance? What does the input impedance look like? The input impedance is primarily capacitive, right? Looks primarily like a capacitor. Over here we have got CGS and there is some CGD, which through Miller effect is going to come, which is through Miller effect is going to be multiplied by the gain of the MOSFET plus 1, and it is going to come in shunt with CGS, etcetera. So, that is how the input is going to look like. As far as the gate itself is concerned, the gate itself is a perfect insulator. So, the resistance is infinitely large looking inwards further. So, this way the resistance is infinitely large. You have got some gate to channel capacitance, gate to drain, gate to source capacitance. Okay. Now, if this is the situation, then where is the power going to be burnt? So, my load looks capacitive. If my load looks capacitive, it is never going to burn any power. So, what maximum power transfer are we talking about? If this is my load, which looks like a capacitor. We are always talking about maximum power transfer, this and that, and how we need to transfer 10 power minus 13 watts onto the MOSFET, the input of the LNA. If this is the situation, then where is maximum power transfer going to happen? The input is looking capacitive. Well, the answer to that, I mean, I am sure this question is occurring in your minds, right? It should occur in your minds if it has not already. The answer to that is that the MOSFET is not completely capacitive. What I have drawn here is not correct. This is not the end of the story. There are a few more things. So, first most important thing that we are forgetting over here is the gate resistance. There is some series resistance associated with the gate. Note series resistance. So, if I want to spread so much charge onto the gate looks like a capacitor. This is the channel beneath the gate, right. So, the gate looks like two parallel plates. Gate is the top plate, the channel is the bottom plate. This is the channel, which is the bottom plate. Okay. Now, if you want to charge the gate to a certain amount of charge, this charge has to travel through this wire and it has to spread all over the gate. And remember that although it is a MOSFET, it is no longer metal oxide semiconductor. This gate is made up of material like polysilicon. So, as a result, polysilicon is also used to make a resistor. So, you can view the gate as if it is a distributed mesh of resistors. Right, some extremely distributed mesh of resistors, and each of these points has capacitance to the channel. So, it is a complicated model, and probably this distributed mesh of resistors and capacitors can be substituted by a model that looks like this, by a simple RC, where C is the capacitance of the gate to channel Cox or whatever CGS or whatever you want over there. And Rg is the gate resistance. So, this is the gate resistance that I am talking about. It is a distributed mesh of resistors all over the gate. In extremely modern technologies, let us say we are talking about 90 nanometers, 45 nanometers, 65 nanometers, 32 nanometers. The gate oxide is so thin that charges actually tunnel through the gate oxide, and that causes gate leakage. Now, in that case, you will additionally get gate leakage. Now, this is not part of our discussion, unfortunately. So, it is your homework to figure out what is going to happen when we are talking about super modern technologies. for older technologies, our situation is that we have a series gate resistance with the gate to source capacitance or whatsoever. So, this R G is what is burning the power. So, this is where you are delivering the power. Now, next question is, we talked about something called power gain. What on earth is this? I mean, I am just giving out terms and you should not blindly accept these terms. What is power gain? What on earth could power gain be? If you think about law of conservation of energy, you are never going to gain in terms of power, right. If you put in, you have a system, you put in so much power, either the power is burnt as heat or the power comes out. Okay. There is nothing else in between going on. Law of conservation of energy holds everywhere. So, the waste power as heat plus the output power should be equal to the input power, right. Traditional network theory, law of conservation of energy tells us all this. So, what on earth is power gain? So, power gain I have defined as P out by P in. I mean, looking at this picture, power gain has to be always less than 1, which means it is not a gain, it is a loss. So, what are we talking about here? Anybody? Any ideas what we are talking about here? Well, this is where you have to put things in a little bit of perspective. We are talking about an active circuit. An active circuit is something that has an additional power supply. So, we have a MOSFET, probably a MOSFET, probably bipolar junction device, whatever you want it to be, anything that is an active component, and power into this system. Let us say this is my system. Power into this system comes from its power supply it has a power supply, bias voltages, bias currents. So, these bias voltages and bias currents deliver power to the circuit. It also comes from the signal or the input. Okay. And power is delivered to the load. So, looking at this, kind of a system, we can say that power gain is P load by P signal and P load plus P wasted. Of course, you want to waste as little as possible, probably want to waste 0. So, now that you see this as your equation, you can conceive of power gains that are more than 1. Now, I have picked this and this out of this equation, and I am saying that P load has to be more than P signal for a power gain to be more than 1. Power gain is basically P load by P signal. So, I am pumping in power from the power supply and that is how the power delivered to the load is going to be more than the power coming in from the signal, right. So, this is the basic idea. This is why this is okay. So far so good. All right. So, with these basic concepts, we are going to close the first module, the introduction module, and we are now going to start the next module of this course, which is RLC networks. So, any questions so far? All right. Okay. So, RLC networks, these are also things that you have studied many times at many different places, undergraduate, postgraduate, even before undergraduate you have probably studied RLC networks. So, the typical RLC network that we are going to study is something that looks like this. And how does this respond? So, if I is a function of omega, what is the relationship between the output voltage and the current, input current? So, to understand this, you use the Laplace transforms, you use traditional techniques, phasors, whatever you want to use, and R, L and C form 3 parallel impedances. So, the combined parallel impedance is 1 by R plus 1 by j omega L plus j omega C. This is the combined parallel impedance. So, V out of j omega by I of j omega is so much, which can be simplified further, and boils down to something that looks like this. Okay. Is this correct? It seems like it is correct. So, how do you know if it is correct or not? At DC, so omega equal to 0, what does our V out by I look like? What does the impedance look like? At omega equal to 0, the inductor is a short circuit. So, if the inductor is a short circuit, then the output voltage should be equal to 0, which means that the voltage output divided by the current is also going to be equal to 0. Okay. So, I plug in omega equal to 0, numerator becomes equal to 0, denominator is R. So, naturally the result is equal to 0. Then the next step is you check at infinitely large frequencies. as omega tends to infinity. As omega tends to infinity, if you look at our network, the capacitor now looks like a short circuit, and once again the response should be 0 volts. So, I plug omega tends to infinity into this expression, and the numerator is infinity, the denominator is r plus infinity plus minus infinity squared. So, in the numerator I have omega, in the denominator I have omega squared. So, net is 1 by omega. So, as omega tends to infinity, 1 by omega tends to 0, which means that z is equal to 0. Okay. So, this is your sanity check, 2 sanity checks. Now, the third important frequency, whenever we talk about L and C in parallel, an important frequency is the resonant frequency. So, we have an inductor and a capacitor in parallel. The inductor stores a current, stores energy in the form of a current, the capacitor stores energy in the form of a charge or a voltage, and these two the energy keeps cycling back and forth between the inductor and the capacitor, and this happens most optimally at the resonant frequency. And at the resonant frequency, which happens to be 1 by square root of L C, what happens at the resonant frequency? So, the first most important thing that you see is that omega squared L C R, when omega is 1 by square root of L C, omega squared L C R becomes equal to R. So, as a result, R and minus R cancel with each other. So, you are left with j omega L times R divided by j omega L. So, you are left with R. Okay. So, it is a very simple relationship. What happens over here? At the resonant frequency, the inductor and the capacitor in shunt form something of an impedance that looks infinitely large. The shunt impedance of an inductor and a capacitor at the resonant frequency is infinitely large. So, you have R in parallel with something that is infinitely large, and as a result the net is R. Okay. So, this concludes our checking. So, this is my expression. Now, ordinarily this should be the end of the story, right, and this is where I should be concluding this module and going to the next chapter, but no, there is a lot to study in this. What we need to look at are the currents going through the resistor, through the inductor and through the capacitor at resonance. So, suppose I apply a current I at the resonant frequency. So, this is I, as I have said. Then presumably at resonance the inductor and the capacitor look like together in shunt look like an impedance which is infinitely large. So, there will be no current going through this section, together they look infinitely large. So, no current goes through to the inductor and capacitor together. So, all of the current I is going to go through the resistor. So, the voltage I have is I times R, and therefore, the current through the inductor and the current through the capacitor at resonance is the voltage by the impedance. And presumably these two should cancel each other, right. I L plus I C should be equal to 0, otherwise does not work, that is Kirchhoff's law. Okay. Now, let us see if that works out. Omega 0 is 1 by square root of L C. So, this is the current through the inductor, and the current through the capacitor is going to be the same with a plus sign, hopefully. Okay, wonderful. So, they match up. The current through the inductor is the negative of the current through the capacitor. Now, what you observe is a factor. So, the current through the inductor, let us look at the modulus of the current through the inductor, which is equal to the modulus of the current through the capacitor, and that is going to be I times R by square root of L by C. Okay. This factor is defined as the quality factor. Actually, that is not the definition of the quality factor, but it so happens that we call this, let us call this Q. Let us call this Q, all right. Now, this number can be anything. You could choose R to be anything such that Q could be 1, Q could be 100, Q could be 0.1. You could choose this quantity to be anything, depending on it, basically depends on your values of R, L and C. Now, let us say Q is 100, in which case what do we have here? We have I being pushed into the circuit, I flows through the resistor, but 100 times I flows through the inductor and flows through the capacitor. Now, that is something amazing, right. You start with a current I and you get 100 times I through the inductor and through the capacitor, right. You can really boost the current to whatever you want depending on the value of Q. Agreed? So, this is something that is not normally captured in this expression over here. In this V by I expression, this fact is not being captured. The fact that the current through the inductor and through the capacitor is some constant times the current that you are pushing in through the resistor, and this constant is a function of R, L and C. It is basically R by square root of L by C, and if you make R very large, then you can make this factor arbitrarily large. the square root of L by C, are you reminded of something from the previous lecture, from the previous module about characteristic impedance? Yes. So, the square root of L by C, this number is somewhat related to the characteristic impedance. So, it has units of ohms and it is a number, it could be something like 50 ohms, in which case if I choose R to be 5 kilo ohms, then I have got a Q of 100. All right. If you want this circuit to work well, the parallel RLC circuit to work well, then you want R to be as large as possible, right, in which case your Q is also very large. Okay. So, this is something very interesting. Now, with this I am going to define Q. What is this Q? I mentioned Q already, but I have not yet defined it, I just called something Q. Okay. Q or the quality factor is defined as the peak energy stored in your circuit divided by the average power, average energy that is burnt. So, this is the definition of quality factor. It is the peak energy stored. Where is the energy stored? Energy is stored in the inductor and in the capacitor. So, at the peak of the crest, at one point of time, all the energy is stored in the inductor, nothing is stored in the capacitor. At some other point of time, all the energy is stored in the capacitor, nothing is stored in the inductor. At some other points of time, energy is shared between the inductor and the capacitor. The amount of energy stored is shared. Okay. Where is the energy consumed? The energy is consumed in the resistor. Of all my circuit elements, R, L, C, mutual inductances, etc., resistances are the only elements that consume energy. Okay. So, now with this as the background, let us try to find out what is the quality factor of my circuit over here. So, if the current has an amplitude of I A, I amp, let us say I amp is the amplitude of the current, then the average power that is being burnt in the resistor, what is the average power that is being burnt in the resistor? So, the average current, so the current through the resistor is I amp, is I, right, which has an amplitude of I amp. So, the average power burnt is equal to I squared, I amplitude squared times R divided by 2. The 2 comes because of the RMS. All right. Okay. What is the peak power that is stored? At some point of time, the inductor stores all the power in the form of a current. At some point of time, the capacitor stores all the energy in the form of a voltage. So, let us look at the capacitor. Both of these energies are equal, right. I mean, when the inductor has all the energy, the capacitor has nothing. When the capacitor has all the energy, the inductor has nothing. Okay. So, let us look at the capacitor. The energy stored in a capacitor is half C V squared, right. The peak amplitude across the capacitor, peak voltage across the capacitor is I amplitude times R. That is the voltage across the capacitor. So, I amplitude times R, that is the peak voltage. At that point of time, this amount of energy stored in the capacitor is half C V squared. So, half C times V squared. All right. So, the ratio of the energy stored to the power being average power being burnt is going to give me the quality factor. So, what is this ratio? This is not right. This has units of time, right. I am dividing a power, I am dividing an energy by a power. So, it will have dimensions of time. So, this can't be right. Okay, what I wrote was correct. Average energy consumed per cycle. This is the average power consumed. All right. So, what is the average energy consumed? No, this is not right. So, please correct your yeah. Okay. So, this is correct now. So, please make this correction. The quality factor is omega times the peak energy stored divided by the average energy consumed, average power consumed. And we are talking about the resonant frequency. So, at the all this computation is valid at the resonant frequency. It is only at the resonant frequency that the current, the power consumed is so much, etcetera, etcetera. So, at the resonant frequency, this is omega 0, which makes it R C by square root of L C, and that is equal to R by square root of L by C. All right. So, this is the quality factor. The quality factor at a given frequency is the omega times the peak energy that is stored divided by the average power that is consumed. Okay. Now, with this in the background, can we now look at series RLC circuits? It is easy to now look at series RLC circuits. The same definition of quality factor applies here. Okay, same old definitions apply. Let us apply a voltage and let us change the configuration a little bit. Let us apply a voltage. Last time we applied a current, now let us apply a voltage, and we are going to measure the voltage that I develop across the resistor. So, this is a resistive divider, right, and this is what we have got. So, that makes it this is my final expression for the output voltage as a function of the input voltage. Now, cross check, sanity checks, when omega is 0, the inductor is a short circuit, the capacitor is an open circuit. If the capacitor is an open circuit, whatever you apply at the input is never going to reach the output. So, the output should be equal to 0 volts at omega equal to 0. Your expression also says the same thing. At infinitely large frequencies, the inductor is an open circuit, which means once again that whatever you apply at the input is never going to reach the output. So, the output should be 0 volts. You look at your expression, you have omega in the numerator, omega squared in the denominator, which means 1 by omega overall. So, at infinitely large frequencies, 1 by omega will tend to 0, which means that you will get 0 at the output. Somewhere in between at the resonant frequency, which is 1 by square root of L C, at this resonant frequency, surprisingly enough, omega squared L C becomes equal to 1. So, j omega R C is in the numerator, j omega R C is in the denominator. So, you happen to get V out is equal to V. So, at the resonant frequency, you expect V out to be equal to V, right, and what is not being told to you is what are the drops across the capacitor and the inductor at the resonant frequency. Now, this you are going to find out, they are going to be equal to Q times V. Actually, there is a J somewhere. But J is irrelevant as far as the magnitudes are concerned. So, one of these will be j q times V, the other will be minus j q times V, and they will cancel out with each other, and you are finally going to see V at the output across the resistor. So, you apply 1 volt at the input, as long as your Q is huge, let us say your Q is 100, you are actually producing 100 volts across the capacitor, 100 volts across the inductor. So, that is something very interesting that happens at the resonant frequency. Once again, energy is shared at between the inductor and the capacitor, and the definition of Q is as before. So, if you look at Q as before, energy stored Okay, let us, instead of writing Q times V, let us do this properly. The current at resonance, the voltage across the resistor is V. So, the current is V by R. So, the drop across L is j omega L times V by R. The drop across the capacitor, actually that is enough, and the current is V by R. So, the energy, the peak energy stored in the inductor is V I squared half L I squared, right. So, the peak energy stored in the inductor is half L times the amplitude of I squared. The amplitude of I is the amplitude of V divided by R. Okay. And the power burnt that is equal to V amplitude V squared by R, V squared by 2 R. So, Q is omega 0 times half L V amp by R the whole squared divided by V amp squared by 2 R. So, 2 and 2 cancel out, V amplitude squared cancels out, and what you end up with is going to be omega 0 times L by R. Okay. And you substitute omega 0 is 1 by square root of L C, what you will get is square root of L by C divided by R. Now, this happens to be the exact inverse of the previous formulation. Previous formulation was R by square root of L by C, this one is square root of L by C by R. Okay. I want you to ponder about these thoughts. So, what we have covered today, first of all we have finished the earlier module. We talked about maximum power transfer, how the source resistance is an integral part of the source, you cannot tamper with it, and maximum power is transferred if the load impedance is the conjugate of the source impedance. It so happens that when maximum power transfer occurs, there is also no reflections. Okay. All right. So, this is the situation that we had for the LNA. If I manage to do maximum power transfer, I do not get any reflections. I also get the maximum output power because my amplifier has a finite power gain. Then we talked about what is this power gain we are talking about, because the input of the amplifier is capacitive primarily. There is also a small resistive component as far as the gate is concerned. Most of this power is coming from the power supply. Okay. So, we will stop here. Thank you.